Greetings. My name is Mrinal, and today me and my group will be talking about our experiential learning project on the topic application of statistics in computational chemistry. These are the topics we'll be looking at today. Let's start off with an introduction to the topic. Computational chemistry. Computational chemistry is a branch of chemistry that uses computer simulation to assist in solving chemical problems. It uses methods of theoretical chemistry incorporated into computer programs to calculate the structures and properties of molecules, groups of molecules, and solids. Computational chemistry has several fields of application, one of which is to identify the correlation between chemical structures and properties. Computational chemistry can only be used when a mathematical method is sufficiently well developed that it can be automated for implementation on a computer. Computational chemistry is not an exact description of real life chemistry, as the mathematical models of physical laws of nature can only provide us with an approximation. However, the majority of chemical phenomena can be described to a certain degree in a qualitative or approximate quantitative computational scheme. Let's look at some topics that are related to our experiment today. Quantitative structure, property relationship, QSPR. QSPR is a computational method that uses molecular descriptors to predict the physical or chemical properties of molecules or materials. By analyzing the relationship between molecular descriptors and the properties of molecules, QSPR models can be developed using mathematical equations. These models can be used to predict a wide range of properties of molecules, such as boiling point, melting point, solubility, and toxicity. The QSPR models involve statistical and mathematical techniques such as regression analysis and partial least squares. Regression models are used to describe relationships between variables by fitting a line to the observed data. In this context, we use one or more molecule descriptors and we can find the chemical and physical properties of an unknown molecule by finding the pattern between the known compounds. Regression analysis. Regression analysis is a set of statistical methods used for the estimation of relationships between a dependent variable and one or more independent variables. In this context, the variables would refer to the known and unknown properties of molecules. It can be utilized to assess the strength of a relationship between variables and for modeling the future relationship between them. Regression analysis includes several variations, such as linear and multilinear regression analysis. Linear regression can be used to model the relationship between a dependent variable and one independent variable. Today, we will be demonstrating the use of multiple linear regression, which is used to estimate the relationship between two or more independent variables and one dependent variable. Here, we can see an example of a linear regression analysis graph. Here are some important representations in linear regression. Multiple R. It is the correlation coefficient that shows the strength of the linear relationship between two variables. R square. It is the coefficient of determination, which is used as the indicator of the goodness of fit. It basically shows the accuracy of our predicted values. Adjusted R square. It is the R square adjusted for the number of independent variable in the model. You will want to use this value instead of R square for multiple regression analysis.
Hello, I'm Ashrit. I'm here to talk about Wiener Index and Zagreb Index. Wiener Index is a graph invariant which is introduced by Harry Wiener in the year 1947. It is defined as the sum of the shortest path distances between all pairs of vertices in a graph. Wiener Index has many applications in many fields like chemistry, mathematics, physics, computer science, and particularly it is used to analyze the molecular structures and predict the properties of organic molecules. It is also used in the study of networks such as social networks, transportation networks. The Wiener index of a molecule is a topological index that measures the sum of the distances between all pairs of molecules in the all pairs of atoms in the molecule. In other words, it is a mathematical representation of the molecular graph that takes into account the distance between all the atoms in the molecule. Here we are going to take an example of N-pentane to understand how Wiener index is calculated for it. We can see that, as we know, pentane is a five carbon compound. We can see that the distance between each atom is calculated beforehand. The distance between atom 1 and 2 is 1, 2 and 3 is also 1, 3 and 4 is also 1, and 4 and 5 is also 1. Whereas the distance between atoms 1 and 3 is 2, 2 and 4 is 2, and 3 and 5 is 2. Next, and the distance between atoms 1 And for the distance between these two atoms is 3, whereas 2 and 5, the distance between these two atoms also 3, and the distance between atoms 1 and 5 is 4. So because they're far apart from each other, thus Wiener index is basically the sum of these all these distances, and we get the sum as 20. Next, we're going to talk about Zagreb index. Zagreb index was introduced by a Croatian mathematician Milan Randic in the year 1991. It is defined as a sum of the square degrees of all the vertices in a graph. Zagreb index, as same, it is almost as similar to Wiener index as it has applications in chemistry, physics, computer science, and many other fields. It is also used in analyzing the molecular structures and prediction of properties of organic compounds. It is also used to study networks such as social networks and transportation networks. We will take an example of n-pentin again to understand how Zagreb index is calculated for it. We know that the degree of each carbon atom is 3. So Zagreb index is basically the square of these degree of these atoms, and we get the Zagreb index of n-pentin is 70. Thank you.
Hi, myself Ishran from AML department. In this topic, we are going to study how to predict the boiling point of an unknown molecule by using QSPR approach. You all know boiling point is the temperature at which vapor pressure of the unknown molecule of the liquid is equal to the surrounding atmospheric pressure. Here we have used machine learning to predict the boiling point of an unknown alkane molecule by training a model by giving the boiling point on molecular descriptors of known molecules, and the machine and the model tries to predict the boiling point of a unknown molecule by fitting a multilinear regression equation curve. In the molecular descriptors can be the molecular weight, number of atoms, intermolecular forces, polarizing power, hydrogen bonding. Here to train the model, we have used one or two molecules with the molecule with the boiling points and their molecular descriptors. Here is the part of the data set we have used. Here is the boiling point, molecular weight, Wiener index, Zappa index. And first, let's see why we have not used a linear regression. You can see different unknown molecule, like different more than one molecules have the same molecular weight. So we can't predict the boiling point just by using a single descriptor like molecular weight. So we have to go for more than one molecular descriptors. Here we have used four molecular descriptors: molecular weight, Wiener index, Zagreb index 1, Zagreb index 2. These three are the topological indices, which helps the model to understand the structure of the molecule. And this is about the general multilinear regression equation curve. This is the boiling point is a dependent variable, molecular weight, Wiener index, Zagreb index, and Zagreb index 2 are the independent variables, and B1, B2, B3, B4 are multilinear regression equation coefficients, and A is the intercept. And this is the partial regression plot. This helps us to understand the influence of each molecular descriptors on the boiling point. And you can see the uh, and here you can see that the influence of a Zagreb index 2 is very less on the boiling point. And this is the uh, plot of this red line is the predicted boiling point, and these blue points are the actual boiling points. And you can see there is less difference between the predicted boiling point and actual boiling point. And this is the multilinear regression equation. And this boiling point is and 69.9927 is our intercept, and 4.1729 0.63 is our regression coefficient. And you can see this is our regression model summary, and the R square value of our regression model is 0.990. That's like our it shows our model is 99% accurate. And here we are trying to predict the boiling point of 3,3 dimethyl pentane with the help of our model. These are the molecular descriptors of 3,3 dimethyl pentane. This is the Smiles notation of 3,3 dimethyl pentane. And And the actual boiling point of 3,3 dimethyl is 359.25 Kelvin. And this is the predicted boiling point 356.757075. And this is the error in the predicted boiling point is 2.5, and the error percentage is 0.69 percentage. 0.69 percentage.
The presentation, and this part is on vapor density using multiple linear regression. The density of a particular gas or a vapor relative to that of hydrogen or with respect to that of hydrogen or air at the same temperature or pressure is known as vapor density. In this topic, we use regression analysis and try to predict the vapor density of random molecule or a hypothetical molecule. For example, of vapor density, acetone has a vapor density of 2 in relation to that of air. That means acetone vapor is twice as heavy as air. To predict the density of a particular molecule, we use regression analysis and the data set provided with known vapor densities and corresponding predictor variables. Predictor variables is the name given to the independent variable used in regression analysis. The predictor variable provides information on associated dependent variable regarding a particular outcome. The predictor variables could include factors such as pressure, temperature, and chemical composition of the vapor. We have gone with two descriptors or predictor variables: molecular mass and boiling point. This is a part of a data set that we have collected, and deals with descriptor and experimental data for vapor density. Running the correlation and regression analysis on of the model using Microsoft Excel, we get the following results. This is the table for correlation between descriptors and vapor density, molecular mass, boiling point, and vapor density. As you can see, vapor density has coefficient of correlation of 0.94 between itself and molecular mass, and the correlation coefficient of 0.775 with respect to boiling point. When we plot the graph, we get the following two graphs. This shows, the blue dot shows the vapor density, and the orange dots show predicted vapor density with respect to boiling point on x-axis. Similarly, molecular mass on x-axis. Here R square refers to coefficient of significance. This shows how well the predicted variables are according to what values that we have found experimentally. Multiple R is coefficient of regression. R square is the coefficient of significance, as I told, and using the coefficients intercepts, we can after running the regression analysis, we get the above table, and using that table we get the equation. Here Vd is vapor density, mm is molecular mass, Bp is boiling point. With the help of above equation, we can find the vapor density of any molecule provided we have the molecular mass and boiling point.
So, rate of diffusion. The rate of diffusion is nothing but the net movement of gas particles from higher concentration to a lower concentration. Here, the formula is given when the volume of the two gases is taken as a constant and compared with each other. That's when we get the square root of molecular masses. This is also called as Graham's law of diffusion. Factors affecting diffusion rate. The rate of diffusion depends upon several factors, including the concentration gradients such as enthalpy, temperature, pressure, and molecular weight of the substance. So there are basically two fixed laws of diffusion. What is fixed law? These are the mathematical equations that describe the rate of diffusion in different scenarios, that is, in real life scenarios and application states. So applications of diffusion. Diffusion plays a critical role in many natural and man-made processes, and it plays a crucial role and a vital role also in nanotechnology, in drug delivery systems, etc. Here we have taken the graph of different gases and their rate of diffusion along with this density and vapor pressure. And so density and vapor pressure here are the descriptors. So when density is plotted against rate of diffusion in this particular graph, you can see that there it has a perfect square fit. But when it's plotted against vapor pressure with the rate of diffusion, we can see it's not the graph is not accurate. This is because the lower value of r, the since the r value is quite low, this in this model predicting the rate of diffusion is not accurate. Predicting the rate of diffusion is possible, but it is not accurate. Uh, this happens due to the data set that is taken is quite low. We have put this model in computational to explain in computational chemistry, because in computational chemistry the data sets, the data values that we take is very much necessary for the accurate or a predictable model to come out. If that is not there, the entire model will not be accurate. So to prove that, we have included this. Thank you.
This is Tanish S from AIML. Today I'll be presenting my chemistry year topics on colorimetry and flame photometry. So, what is a colorimeter? A colorimeter is a device that is used in colorimetry. This refers to a device that helps in specific solutions to observe a particular wavelength of light. The colorimeter is usually used to measure the concentration of a known solute in a given solution with the help of Beer's-Lambert's law. The colorimeter was invented in the year 1870 to determine the measurement of the light transmitted. The above formula IO is equal to IR plus IA plus IT is used. This is the graph of colorimetry. So as you can see, it is linearly dependent on volume of CuSO4 and absorbance. This was a prime example of perfect correlation. This was an experiment done in the chemistry lab, and we used the below formula and we can predict the absorbance. Flame photometry. So what is a flame photometer? A photoelectric flame photometer is an instrument used in inorganic chemical analysis to determine the concentration of certain metal ions. Among them, sodium, potassium, lithium and cadmium, group 1 and group 2 metals, are quite sensitive to flame photometry due to their excitation energies, low excitation energies. This is the graph of flame photometry. This, as you can see, it is linear, it is also linearly dependent, and it has the volume of NaCl against the photometric reading. This process is also used in clinical laboratories and for determining sodium, potassium, lithium and calcium ions in body fluids. This data has been got using statistics. Some societal impacts of applications of statistics in chemistry. One of the historical QSAR applications was to predict boiling points. So QSPR is used in green chemistry for risk management. Computational approaches help in the efficient synthesis of compounds. Computational approach to design molecules that interact in specific ways with other molecules. Example, drug design and catalysis. The basic strategies of QSPR is to find an optimum quantitative relationship which can be used for prediction of the properties of compound, including those unmeasured. QSPR or QSAR analysis is widely used tool for improving knowledge in the fields of natural science such as chemistry, biochemistry, medical chemistry and nanochemistry, as well as chemical technology and ecology. By this we come to the end of the presentation. So in conclusion, the integration of statistics and computational chemistry has been provided a powerful toolset for analyzing and interpreting large amounts of chemical data. Through the use of statistical methods, researchers can extract meaningful insights and correlations from the complex chemical systems. Additionally, computational chemistry techniques can provide accurate predictions of molecular properties and behaviors. Combination of these two fields has a potential to revolutionize our understanding of chemical systems and accelerate the development of new materials and drugs. These are the sources. Thank you.